Hello my friends, welcome again to my video channel. Today we'll start a new project, the Peggie. This little thing here, Peggie. What is Peggie? The company is Accord and the name of the model, the brand name is Peggie. It's an AM radio built in 1957. Presented on the market 1957. It is said to be the first German-made fully transistorized radio. In those days there were mixed radios for portable use, used with small tubes and transistors and semiconductors in it, but this is fully transistorized, only for medium frequency range. There was another company in Germany, it is Telefunken. They also presented a radio in this year, but it is said that this was a little bit earlier. It was published earlier than the Telefunken, so it is said to be the first one. Okay, and it could be bought in this year. I'm not a referee. I do not decide what is right and what is wrong. I only can say it was this year. The first transistorized radios were on the market in 1954, as I found in USA. There were some models, but this one is the first here in Germany. So let's have a look at it and have a look at some details. This radio, when you're interested, look in the net for Accord and Peggie. The price, Deutschmark, 189 in 1957. This was a lot of money in those days. The average salary of a worker was 400, 500 Deutschmark per month. So when they had 5,000 up to 6,000 Deutschmarks per year, then it was a good salary. I also remember my father when he started working in those days. He also had only 600 Deutschmarks. He was an engineer. So this is a lot of money, which had to be paid for it. And it's only a small transistorized radio for AM and for medium wave range between 550 kHz and 1600. Let's have a look at some technical details. It's a superhead, 5 transistors, germanium transistors. There's a frequency range 515 to 1620. 9-volt battery, plus is connected to ground because these transistors are all PNP transistors. The case is made of leather. Yes, standard radio, we would say today, nothing exciting. Let's have a short look into the schematic. That's a ferrite antenna, and this is a self-oscillating mixer. Here we have the oscillator stage, the mixer stage, and this is the first diode, this is the first attenuator. This radio has an AGZ. It's an interesting circuit. When the output of the detector increases, gets more positive, then this transistor gets blocked. It's a PNP transistor, and this voltage here gets more negative because we have here minus 9 volt, and this means this diode gets conductive because the anode is connected directly to this point, which is rather, it's 1K, 8K, it's approximately minus 8 volt. The diode is blocked for low input levels, and for higher input levels this diode D1 gets conductive. The threshold is set here with this pot, which controls also this transistor. So this is the first attenuator. When the signal gets strong, this diode gets conductive, and this is the first IF circuit, which is then damped. The AGZ, it's a trick here with this AGZ voltage. Here we have the second amplifier, and here we have the detector, and this is the output to the lock. That's the AF setting, volume setting, goes to the transistor. This transistor is output. And here we have a third diode. when I first saw this diode, I thought, oh, what is this diode? Well, it's a very tricky circuit. Never seen it before. This is a typical Class A amplifier. It's not a push-pull configuration, it's a Class A amplifier, but Class A amplifiers have one disadvantage. They have a high power consumption, high relative for a battery. So the bias is set to Class B operation with this resistor. Sorry, yes, with this resistor and the capacitor here. Here, these two resistors. This is a voltage divider. Here the negative voltage goes to the base of T5 at low output levels. And when the output level increases, when we increase the setting of the volume, then we have here more output power, and then here we have here more voltage, and an additional negative voltage is added to the base of this transistor via this capacitor. This capacitor is charged up and generates more negative voltage for T5, and then T5 gets more conductive. So the bias of this transistor is shifted from Class B for low output levels to Class A for higher output levels. And when the output level decreases again, when the music stops, this voltage here drops, and the transistor is again in Class B operation. This reduces the current consumption of the AF stage considerably, and the battery lifetime is prolonged. The manufacturer says about 35% or so. So this diode is a very tricky method to reduce the current consumption for this output stage. I've never seen such a circuit, but it's very interesting. I'm sure the THD is not the best of the circuit, but the speaker also is not the best. So I think it is not relevant whether there are additional distortions on the signal or not, but this circuit, to save battery, it's a little bit more important. Let's have a look inside. We will open it on the rear side. Two knobs can be opened. Here is a place for the battery. It's a 9-volt battery. In those days there were bigger 9-volt batteries on the market than today, not our standard 9-volt small block we have. There were bigger 9-volt batteries on the market, but it's not relevant for the moment. This can be taken off. Okay, the flaps are broken. Well, now we see the interior of this radio. This flat rod is a ferrite antenna. It's not round, it's flat. These are big electrolytics. I think they are not okay. They have to go. 3 diodes we have seen. The schematic, the transistors are obviously on the other side. There are sockets for the transistors. So the transistors are socketed. Rather close together. Could be shorted. This is the pot. One pot for setting. It is fixed with some glue. What is this? Okay. We will see. I have to check it and try to take out the whole chassis. All components look as they have been stolen from a tube radio. In those days it was of course difficult to get components for transistorized radios, so the volume and the ratings are more or less for tubes and not for transistors in those days. Yes, I will take out the chassis. I try to take it out and then we can continue. The chassis is out. We have one screw here which is fixed on this tab. We have a second screw which is not existing in this radio, which is shown here, and then the knob of course has to be taken off, the tuning dial, and then it can be flipped out, and then we have access to the whole unit, and then there's nothing in it except some dust, but it looks rather clean. Okay, nice, very nice. It's leather. It's completely leather, not wood. No, it looks like leather. There are 1, 2, 3 layers of leather. And some paper inside, of course. But the case, the complete case, is made of leather. Interesting. Signs of a bad battery. It was a small block, not the big one. Foam. The foam is brittle. Ooh, boop, boop, boop. Yes, has to be replaced. Yes, but the whole case is leather. Nice, very nice. Like it. I love it. The first step before I switch on this unit, I will swap all electrolytic caps. Totally I found 7. I counted them also on the board. These are the values. The voltages are rather low. 3 volt, 3 volt. Okay, we take bigger ones, not less than 12 or 16 volt DC. The value is 1.25 microfarad. Is a little bit strange. I will take 1.5, 2.5, 2.2 or 4/7. This is 2.5. Yes, this electrolytic cap, which is the part of this interesting circuit for the AF amplifier. Maybe a little bit an increase of this time constant could help for better sound when the transistor switched on, to reduce the time constant or increase the time constant. Could be better. Okay, I will do this in the next step and show you the result. All electrolytic caps are replaced. These are the old ones, the new ones, here, here. This one, and 2 are on the other side. Now I will check them, just for curiosity, how good or how bad they are. This one should have 100 microfarad. It has 200 microfarad. And the quality factor is acceptable, 5. Okay, but I think there's an isolation problem. Such overperformers are always suspicious. Regarding isolation, this one should have, what should it have? Also 100 microfarad. Quality factor of 1. Okay. Very lossy, very lossy. 180 instead of 100. This one should have 32 microfarad. Well, let's look at this one. Don't know, I think it was a 10 microfarad. Yes, quality only 3. I will check the isolation of these electrolytics. This one is in the range of 700 kilo ohms. Okay, has to go. What is this one? One of the 100 microfarads, which looked to be an overperformer. 9 mega ohm. Okay. Not so bad. Not so bad. Maybe the problem is a serial resistance. Let's take this one. This is plus and this is minus. 30 mega ohm, 26. Maybe the ESR is a problem, not only the isolation. Maybe they are all dried out. Okay, this one should have 10 microfarad. It has an ESR of 35 ohms. A little bit too high, a little bit too much. Let's have a look at this big one, the 100 microfarad. It had more capacity than specified. Four ohm ESR. That's also too much. Okay, we should consider that all these electrolytics are about 0.7 ohms, are about 60 years old. It was built in the late 50s or early 60s. So these capacitors are all old, dried out. Well, it was surely a good idea to swap them all. Only 7 electrolytics, not a big deal. Now we can go to the next step. I cleaned the pot, connected 9 volt, and then we have reception, we can hear something. I'm in a basement here without external antenna, it's evening. Okay. It makes some noise. Well, this indicates that all transistors are okay. Maybe some of the resistors drifted away. There are types in it which are not very reliable after 60 years. I will check the resistors and try a new alignment of the IF stage 455 kilohertz. Maybe if there's a drift also. The frequency range in general seems to be okay. I have to check it whether the range is okay. But I think we have no big issues any longer. After the check of the resistors, I couldn't find any wrong resistor. It's a check of the bias of the D1. Sorry, the D1, which is the attenuation. And D1 has to be without input signal fully open. That means the anode has to be more negative than the cathode. This is a damping diode for the first IF circuit, as we have discussed. So it's important to look whether the diode is in forward or in reverse direction polarized. And when I take my voltmeter, I can see that we have a voltage of approximately 0.8 to 1 volt in reverse direction. That this diode is reverse polarized. That means that this resistor here is adjusted okay, and the adjustment is still okay. So I do not touch it. I don't swap any resistors. I don't swap this setting here. And now I will try to optimize the IF chain with a 455 kilohertz signal. Now the alignment of the 3 IF stages. I feed in a signal in the ferrite antenna with a small coil, 455 kilohertz, and align or tune this circuit to 520 kilohertz, so the signal goes rather undamped through it. And then I can align this, and this to maximum, because the first transistor also is an amplifier, not only a mixer or oscillator. It's also an amplifier for this frequency when this circuit is tuned to the lowest possible AM frequency. Then I can align this, and this. The scope is connected to the speaker. The signal is very low, so the AGC is not affecting it. And now I can align the 3 cores for maximum, and I found they are at maximum. One, 2 and 3. I repeat it several times. Okay, the first one is not so critical. Well, the next step is to check the frequency range. By the way, I've forgotten to show you the coil. I made here a small coil, 3 turns enabled copper wire isolated, and then it can be fed over the ferrite core, the ferrite rod antenna, and then we have the signal. The signal generator is set to 550 kilohertz at the lower end, and I can align it. Here at the end you see 550, and the maximum is 1600 something. You go up to 650. Yes, that's it. Okay. This is okay. The frequency scale, I didn't touch it, so there is no need or no assumption to assume any problems. And the IF cores were also at their maximum setting, just to check it. This is approximately 700 kilohertz. Sorry. This generator is not the best for this work. Okay, 700. Measurement of the supply current for this scale is 10 milliamps. Without AF output we have approximately 8 milliamps. I tuned my signal generator to 1 megahertz, 1 kilohertz AM modulation, and when I increase the volume we are reaching 10 milliamps. At this range there's no increase seen. I think this is caused by the circuit which shifts the bias of the AF from class B to class A. We have higher output levels and of course higher currents, so this is an indication that we are approaching class A operation. Well, now let's do some receive experiments in the evening or at night. We do not have so many AM stations in Europe here. The number of AM transmitters in long, medium and shortwave range is decreasing. Many companies think it's not necessary to have AM. I have a different opinion, but the beam counters in many companies are too much and too strong, so such stations are shut down, antennas are unmounted. It's a pity, but there are many things going wrong on this planet. And now a little test setup. Little sister, Peggie, and big brother, Grundig satellite. It's late in the evening, or better said early in the morning. AM station. I found one on the lower end, a weak station. Don't know which station it is. 638 kilohertz. Chosen is maximum bandwidth. This is identical to the bandwidth of this Peggie. Not so bad. The difference is mainly the speaker. But in general the reception is not so bad. From the little sister Peggie. Let's look for another station. 790 kilohertz. 1175. Music from those days. Image walking on a street with this radio in those days and this music. Okay, that's stylish. That's the end of our project, of our little trip with this small radio with Peggie. And when you compare the reception from the Peggie and from the Big Brother Unix satellite, okay, it's a little bit more sensitive, less noisy. This radio is noisy. I think the transistors are bad. These old germanium transistors create some noise. Maybe also the carbon resistors in it. I assume both make or generate some noise. This receiver is a little bit, okay, not perfect, but seen for its age and for the simplicity of the circuit, it's rather good. This radio here has 3 transistors in the front end. One transistor is for RF amplification. That means the ferrite rod. Then there's a transistor for amplification and a second selection circuit, a resonance circuit. The second transistor is a mixer itself. And the third transistor is oscillator. So this radio has 3 transistors in the front end. This has only one. Self-oscillating mixer, which acts also as amplifier. Okay, this concept will have problems with strong nearby radio stations, but we do not have this case in Europe any longer. It was decades ago when we had a lot of strong AM stations. There are not so many stations in the air. Well, it's not for daily use, of course. The alignment of this with this wheel is very, very difficult, very, very touchy, and it really makes no fun to tune it into a station. Anyhow, I think it was a nice trip. This radio is a part of history, especially for German radios. 1957, this radio is developed 2 decades later. End of 70s. That's the end now. Stay healthy, stay tuned, and see you on this channel.